We'll start in 1 minute. Today we'll start the test 1 review. Remember, test 1 is this Friday. It will be proctored on Zoom, and I'll send more information today or tomorrow about a Zoom orientation meeting that we'll have for test 1. On the test 1 review sheet, I don't think we have enough time to work out every problem to its completion, so I'll start out by setting up each of the problems and then leaving the rest of that for you to do. After class on Wednesday, after tomorrow's class, I'll send the answers to the test 1 review sheet. In this first problem, it says use integration by parts to evaluate. Well, one way to do it is let u be x squared plus 1, so that du is 2x dx, and dv is e to the negative 2x dx, and that means v is negative 1/2 e to the negative 2x. Okay, so u times v, I'll write it as negative 1/2 the quantity x squared plus 1 times e to the negative 2x. And then from that, we're subtracting the integral of v times du. So if beforehand we multiply 2x dx by negative 1/2 e to the negative 2x, that simplifies to negative x e to the negative 2x dx. So if I'm subtracting a negative, I'll just write it as adding a positive. So we're going to add the indefinite integral of x times e to the negative 2x dx. Then we have to use integration by parts a second time. So let's get started on this one. Integration by parts on this one, let u be equal to x this time. So du is equal to dx. And if dv is e to the negative 2x dx, then v is negative 1/2 e to the negative 2x. So it looks like we're going to do this one pretty much to its completion. So I'll rewrite this, negative 1/2 times the quantity x squared plus 1 times e to the negative 2x. And then we're going to add the result of integrating this by parts. So we're going to add negative 1/2 x times e to the negative 2x. So since we're adding a negative, I'll write minus 1/2 x e to the negative 2x. And then we're going to subtract the integral of v du. So once again, we're subtracting a negative, so I'll just write it as plus, and then the factor 1/2 out front, and then times the indefinite integral of e to the negative 2x dx. Okay, I'll leave the rest of that for you to do. There's just one more simple integral to evaluate on this one. Yeah, the next few problems under number 2, compute the partial fraction expansions of the rational functions below. So this first rational function, x plus 2 over x times x minus 1 times 2x plus 1, the factors in the denominator are all linear, so we can write the expansion as a over x plus b over x minus 1 plus c over 2x plus 1. And then with the common denominator of x times x minus 1 times 2x plus 1, well, we would have to multiply a times the denominator x minus 1 times the other denominator 2x plus 1. And then multiply b by x times 2x plus 1. And then multiply c times x minus 1. And this is all over x times x minus 1 times 2x plus 1. Okay, if we clear denominators, that is, so for the moment, we're ignoring this middle part. And if we multiply both of these terms by the common denominator, all of those denominators will cancel and we'll get the equation x plus 2, that's this numerator, equals this numerator. But in the next step, I'll do some multiplying. So we're going to have a times the quantity we get when we multiply x minus 1 times 2x plus 1. So that will be 2x to the second plus x minus 2x is minus x, and then minus 1. Then in the next product, bx times the linear factor 2x plus 1, we get plus 2bx to the second plus bx. And then cx times x minus 1 is cx to the second minus cx. And we'll take this a couple of steps further. I guess we'll distribute multiplication by a here. So we get 2a x to the second minus ax minus a plus the rest of this plus 2bx to the second plus bx plus cx to the second minus cx. And now we'll collect like terms. There are 3 terms that have x to the second, and the coefficient is 2a plus 2b plus c, that quantity times x squared. There are 3 terms with x in it, so I'll write it as plus the quantity negative a plus b minus c times x. And there's only one constant term. It's the minus a. Okay, so I'll write down the system of equations that you have to solve for a, b, and c. The left-hand side doesn't have an x squared term, so that means this coefficient, 2a plus 2b plus c, has to equal 0. 2a plus 2b plus c is 0. On the left-hand side, the coefficient of x is 1, so that means the coefficient of x on the right-hand side is also 1. So negative a plus b minus c equals 1. And the constant 2 is equal to negative a. So I'll just write negative a equals 2. Okay, I'll leave the rest of that for you to do. Solve for a, b, and c, and then after you know what a, b, and c are, replace a, b, and c up in that expansion. Okay, the next problem, the next rational function, f of x equals x to the third divided by x minus 1 times x plus 2. Okay, so to compute the partial fraction expansion of this rational function, first we have to long divide the numerator by the denominator, because the degree of the numerator is bigger than the degree of the denominator. So the denominator, when you multiply those two linear factors, you get x squared plus x minus 2. And we're going to divide that into the numerator, x to the third. So x squared goes into x to the third x times. And then x times x squared plus x minus 2 is x to the third plus x squared minus 2x. And then we subtract. X to the third minus x to the third is 0. 0 minus x to the second is negative x to the second. And 0 minus negative 2x is plus 2x. And then there's one more cycle in the division. X squared goes into negative x squared, negative 1 times. So negative 1 times the divisor is negative x squared minus x plus 2. And the remainder will be 2x minus negative x is 2x plus x, or 3x. And 0 minus 2 is minus 2. Okay, so what that leaves us with is the quotient x minus 1 plus the remainder 3x minus 2 divided by the divisor x squared plus x minus 2. But I'll write that in factored form, x minus 1 times x plus 2. Okay, then we want to find the partial fraction expansion for this, the 3x minus 2 over x minus 1 times x plus 2. So we'll do that separately. Just remember that in the final answer, this x minus 1 is part of the expansion. But we're going to look at this by itself. So 3x minus 2 over x minus 1 times x plus 2. The two factors in the denominator are both linear, so we can write the expansion as a over x minus 1 plus b over x plus 2. And then adding these two terms with a common denominator, we're going to get a times x plus 2 plus b times x minus 1 over the common denominator x minus 1 times x plus 2. Okay, then after clearing denominators, the 3x minus 2, sort of running out of space, 3x minus 2 is going to be, we can combine a little bit of the work here. We're going to have ax plus bx, so I'll write that as the quantity a plus b times x. And then two constants plus 2a minus b. So in this one, it has to be the case that a plus b equals 3. Those are the coefficients of the x term. And then the constant negative 2 equals 2a minus b. So I'll write 2a minus b equals negative 2. And then you can solve this for this system for a and b. Okay, in part C, well, we can proceed to write the expansion. The degree of the denominator is 4, the degree of the numerator is 1. This time we have a linear factor x minus 1 to the second. So in the expansion, we have a over x minus 1, and then plus b over x minus 1 squared. And we have a irreducible quadratic factor x squared plus 1. So for this one, we need cx plus d over x squared plus 1. We can clear the denominators from this step if we just multiply every term on both sides by the least common denominator. We'll be left with 3x plus 1 on the left-hand side. On the right-hand side, we'll have a times 1 factor of x minus 1 and times the irreducible quadratic factor. And then we have b times just the irreducible quadratic factor. And finally, cx plus d, we have to multiply that quantity by x minus 1 squared. And let's take it a little bit further. So we'll multiply x minus 1 times x squared plus 1. We're going to get x to the third minus x to the second plus x minus 1. And then the next one, bx squared minus b. This product on the right, cx plus d, when we square x minus 1, we get x squared minus 2x plus 1. Okay, a little bit further, 3x plus 1. And then a times x to the third minus ax to the second plus ax minus a plus bx squared minus b. And then here we have cx times x squared, so we'll get cx to the third, and then minus cx squared minus 2 cx squared, and plus cx times 1, and then plus dx squared minus 2dx plus d. Okay, I think I'll leave the rest of that for you, unless you have questions about how to proceed. Oh, okay, I'll do one of them. For the x to the third term, the left-hand side doesn't have an x to the third term. So that means the coefficients of the x to the third term on the right-hand side have to add up to 0. And there are only two terms that have x to the third, ax to the third plus cx to the third. So the coefficient a plus c has to be 0, and so on. Okay, the part D. Oh, there's a note online. Shouldn't it be plus b instead of minus b? And that is correct. B times x squared plus 1. This should be plus b and plus b there. Yep, that's right. Okay, for this one, we have degree 3 in the numerator and degree 5 in the denominator. So the partial fraction expansion, there's one linear factor, x minus 1, so we have a over x minus 1. And then we have an irreducible quadratic factor squared, so we have to have bx plus c over x squared plus 1, and then another term, dx plus e over x squared plus 1 quantity squared. Okay, when we clear the denominators, which is what you get when you multiply every term on both sides by the least common denominator, the left-hand side will become x to the third minus 9. And when we multiply a over x minus 1 by the least common denominator, we'll get a times the quantity x squared plus 1 squared. And then multiply the middle term by the least common denominator, we'll get bx plus c times x minus 1 times 1 of the irreducible quadratic factors. And then the last term, we just get dx plus e times x minus 1. Okay, I'll leave the rest of that for you to do. Just expand the right-hand side, combine like terms, and then observe what the coefficients must be equal to based upon what's on the left-hand side. And the next problem, number 3. This one won't be so hard because all we're going to do is write down the forms without finding the actual values of the letters. Okay, so we don't have to do long division because the degree of the denominator is 7, and the degree of the numerator is 5. Okay, we have an irreducible quadratic factor x squared plus 1 squared, so the partial fraction expansion starts out with ax plus b over x squared plus 1 to the first, and then cx plus d over x squared plus 1 to the second. And then we have, in the denominator, we have a linear factor to the third power. So we just need a constant e over 2x plus 1, and then another constant f over 2x plus 1 to the second. And then finally, a constant g over 2x plus 1 to the third. And that's all we're supposed to do on this one. Okay, in part B, the degree of the denominator is 9, and the degree of the numerator is 10. So what we should do then is multiply all of those factors in the denominator and then divide the numerator by that, and then write the remainder over the divisor, and then write the expansion after that. Well, we won't do all of that work, but supposing we do the long division and we have this denominator, we still have this denominator regardless. So let's just write the partial fraction expansion that corresponds to this denominator. We have the linear factor x minus 3 to the second. So that means we'll have a over x minus 3 plus b over x minus 3 to the second. There's another linear factor, x plus 1, but this one's raised to the third power. So we'll have c over x plus 1 plus d over x plus 1 to the second plus c over x plus 1 to the third. And we have an irreducible quadratic factor squared. So we still need 2 more terms. One will be fx plus g over x squared plus 1. And then finally, the last one, h times x plus capital I over x squared plus 1 squared. Okay, so that's all we'll do on that one. Okay, that brings us to problem 4. We have a bunch of indefinite integrals. So the indefinite integral of x to the third times the natural log of x dx. Well, we've seen problems sort of like this a couple of times. So I would use integration by parts. So I will pick u to be the natural log of x. So I'll make a note of that, integration by parts. So if u is the natural log of x, then du is 1 over x dx. And dv is x to the third dx. So v is x to the fourth over 4. Okay, then apply the integration by parts formula, u times v, the natural log of x times x to the fourth over 4. I'll write it as x to the fourth over 4 times the natural log of x. And then minus the integral of v times du, so x to the fourth over 4 times 1 over x dx. And you can see this one works out really nicely. So it won't take long to get this one. So when we simplify this, we just have x to the third over 4 dx. And then the last step, x to the fourth over 4 times the natural log of x minus x to the fourth over 16 plus a constant. Okay, part B, the indefinite integral of x to the second times sine of 3x. Hey, what method do you want to apply on this one? Yeah, integration by parts looks like the best thing to do. So when we use integration by parts, we usually want set u to be equal to something that will get simpler when you take its derivative. So if we assign u to be x squared, which is a degree 2 polynomial, the derivative is degree 1, which is simpler. So du is 2x dx. And then dv is sine of 3x dx. And v is negative 1/3 cosine of 3x. Okay, so the integration by parts formula, u times v, I'll write it as negative 1/3 x squared times cosine of 3x. And then minus the integral of v times du. So we're going to be multiplying 2x dx and negative 1/3 cosine of 3x. So we're subtracting a negative, so I'm going to write plus, and then the constant 2/3 I'll write in the front. And then the remaining terms inside the integral are 2x times cosine of 3x. Okay, then this part, let's look at this separately. We're going to integrate that by parts also. Oh, yeah, the 2. That's what you were saying, right?
Yeah.
Yeah, I already brought the 2 out, so. Okay, yeah, it's the indefinite integral of x times cosine of x. Okay, so integrate this by parts. So u is x and du is dx. dv is cosine of 3x dx, and v is 1/3 times sine of 3x. Okay, so u times v, this one's 1/3 times x times sine of 3x, and then minus the integral of v du. So that's going to be minus 1/3 times the integral of sine of 3x dx. So we might as well finish this one, and then afterwards we'll put it up there. So this is 1/3 x times sine of 3x. The integral of sine of 3x, or an antiderivative of sine of 3x, is negative 1/3 cosine of 3x. So this is minus 1/3 times negative 1/3. So this will be plus 1/9 times cosine of 3x, and plus a constant. So we'll put this quantity inside those brackets up here. We're going to multiply that quantity by 2/3, so we can go ahead and do that in this step. 2/3 times 1/3 x sine of 3x is 2/9 x times sine of 3x. And then 2/3 times 1/9 is 2/27 plus 2/27 times cosine of 3x. And then plus c. Okay, so we did the whole thing on that one. Okay, the next one, part C. The indefinite integral of cosine of x to the 7th times sine of x to the 3rd dx. So on this one, well, there's a couple of options, but one might be simpler than the other. If we rewrite sine of x to the 3rd as sine of x to the 2nd times sine of x, then we'll use the fact that sine of x squared is equal to 1 minus cosine of x squared. And then also, if we assign u to be cosine of x, then du is negative sine of x. And then after that, we'll be able to use the substitution rule. So first, replace sine of x to the 3rd with sine of x to the 2nd times sine of x. We'll replace sine of x squared using the Pythagorean identity. It's 1 minus cosine of x squared. Let's go ahead and multiply those quantities. So we have the, in parentheses, cosine of x to the 7th minus cosine of x to the 9th times sine of x dx. Okay, then using the substitution rule, if we assign u to be cosine of x, then du is negative sine of x dx. We have the sine of x dx. We just need to multiply by 1 in the form -1 times -1. So when we do that bit of transformation, we'll end up with the negative of the indefinite integral of u to the 7th minus u to the 9th du. So we'll get the negative of u to the 8th over 8, and then the negative of a negative is positive u to the 10th over 10 plus c. And then the last step, replace u with cosine of x. So negative cosine of x to the 8th over 8 plus cosine of x to the 10th over 10 plus c. Okay, let's look at the next page. The indefinite integral of x to the 3rd over x squared minus 4. Okay, what do we do to start on this one? So it's a rational function. The degree of the numerator is x to the 3rd. The degree of the denominator is x to the 2nd. So long division is what we do first. So we divide x to the 3rd by x squared minus 4. X squared goes into x to the 3rd x times x squared minus 4 is x to the 3rd minus 4x. And then when we subtract, x to the 3rd minus x to the 3rd is 0. 0 minus negative 4x is 4x. Okay, so we can rewrite this as the integral of the quotient we get from long division, which is x, and then plus the remainder 4x over the divisor x squared minus 4. We can proceed, well, we all know what the antiderivative of x is, but for the antiderivative of 4x over x squared minus 4, we can proceed in a couple of ways, well, probably 3 ways. What do you think is the easiest way to find an antiderivative of 4x over x squared minus 4? Yeah, u substitution. If you let u be equal to x squared minus 4, then du is 2x dx. Well, we can think of 4x as 2 times 2x, and then use substitution. So I'll rewrite this as a sum of 2 integrals, the indefinite integral x dx, and then plus 2 times the indefinite integral of 2x over x squared minus 4 dx. So this 2x dx over x squared minus 4, that has the form du over u. And the integral of du over u is the natural log of the absolute value of u, right? So I can write that down if anybody wants to see it, or I'll just otherwise I'll just do it directly. The antiderivative of x with respect to x is x squared over 2, and then plus 2 times the natural log of the absolute value of x squared minus 4 plus c. Okay, part E. The indefinite integral of 5x minus 3 over x to the third plus x dx. So what kind of function is the integrand? The 5x minus 3 over x to the third plus x. It is a rational function, so if you have an integrand that's a rational function, you should at least think, well, can I do, what do we call that? The partial fraction decomposition? Can we apply partial fractions? Yeah, probably. So let's rewrite this as 5x minus 3, the integral of 5x minus 3 over x times x squared plus 1. So over here on the side, we'll look at the expansion, 5x minus 3 over x times the irreducible quadratic factor x squared plus 1. So the partial fraction expansion will have the form a over x plus bx plus c over x squared plus 1. If we clear denominators, multiply every term on both sides by x times the quantity x squared plus 1, we'll get 5x minus 3 equals a times the quantity x squared plus a. I'll just write it out as ax squared plus a, and then plus bx plus c times x, which is plus bx squared plus cx. Ax squared plus bx squared Okay, let's write it one more step. So the coefficient of x squared is a plus b. The coefficient of x is c. And then plus a constant a. So a plus b has to be 0. The value of c has to be 5. And the constant a is negative 3. And since a plus b is 0, b has to be positive 3. Okay, so we can rewrite this indefinite integral. The value of a is negative 3, so negative 3 over x. And I'm going to write separate integrals. Instead of 3x plus 5 over x squared plus 1, I'm going to write it as plus 3x over x squared plus 1, and then plus 5 over x squared plus 1. Okay, so the antiderivative of negative 3 over x is negative 3 times the natural log of the absolute value of x. And then we can use the substitution rule on this one. If u is x squared plus 1, du is 2x dx, and we have a 3x, and 3 halves times 2x is 3x. So the next integral, the next what we get when we evaluate the middle integral is plus 3/2 times the natural log of x squared plus 1. And then what about the integral of 5 over x squared plus 1? So that's going to be 5 times the inverse tangent of x plus c. Okay, we're about out of time. So tomorrow I might need to pick up the pace a little bit so that you can at least see how to start the rest of those. But that is all for today. Go ahead and sign in for attendance.
Have a good day.
You too.